Thank you. So first of all, I'd like to thank the organizers for inviting me. I have enjoyed this conference very much, and I'm very happy to be here in Oaxaca. It's my first day in Mexico, and I'm glad that it's here in this city, which I like very much. So for long, my title has been TBA, so I tried to figure out what that meant, and I came up with tensor functors behave algebraically. But it's more of a slogan, so the true title is Hopf-monads, Illustration and Related Notions. That's more serious. A little bit of terminology to begin with. So if a tensor category is a monoidal category which is at the same time, which has duals, and it's at the same time it's a billion k-linear category. And there are some compatibilities between the monoidal structure and the linear structure. And there is a local finiteness condition, which is here. And we say that it is finite if it's linearly equivalent to the category of finite dimensional modules of a finite dimensional algebra. So you had different definitions, but they are equivalent. And a fusion category is a special case. It's a semi-simple finite tensor category, at least when the field is algebraically closed. A tensor functor is a functor between tensor categories, which is k-linear, which preserves the monoidal structure, and which is faithful exacts. So if the category D is fusion, that's automatic. You don't have to assume it. And I will consider certain objects, the trivial objects. That's the objects which are sums of units. And they form a tensor subcategory, which is equivalent to the vector spaces. So they will play a role at one point. And the kernel of a tensor functor is the subcategory of the source category of those objects which are sent to trivial objects of the target category. So that was the terminology. And now, let me see. Okay, so in order to motivate the introduction of Hopf-monads, which is an object we introduced with Alexis Verlisier some time ago, I will consider the following problem, which was our initial motivation. So I do not control things very well. The question is, can the Drinfeld center be described algebraically? So that was our problem. We needed that to compare certain topological invariants. For some reason, we needed an algebraic description of the Drinfeld center. So what do I mean by that? So the Drinfeld center, we have met it already several times. You start with a monoidal category. I assume that it has duals. And the Drinfeld center is a braided category with duals. And there's a forgetful functor from the Drinfeld center to C. And objects of the Drinfeld center are so-called half braidings. So an object plus a half braiding. And you forget the half braiding, and you get an object of C. And that's strict monoidal. So we would like to describe this situation algebraically. So there's a special case when C is braided and has a coend. So we have already met the coend. It's written like an integral like this. So if you're not familiar with coends, just assume the category is fusion, and then it's just a sum indexed by simple objects. Then Majid showed that the coend is a quasi-triangular Hopf algebra in the category C. So since C is braided, there's a notion of Hopf algebra in C, and the coend has such a structure. And then one can show easily that the center of C is just the category of C modules. Sorry, not H modules, C modules. That's the category of modules over the coend. And since the coend is Hopf and quasi-triangular, that's a braided category, and they are equal or isomorphic as braided categories. So that's what I call an algebraic description. And we would like to have something like that, when the category is not necessarily braided. And the first problem is that there are no reasonable, there are no Hopf algebras in a non-braided category. So one can try some things, but it does not work, as I will show later. So we would like to describe the center as the category of Z modules. And what is this Z? So it turns out that Z exists, but it is a quasi-triangular Hopf monad. So I will try to explain a little bit, without defining Hopf monads, I will try to explain how we get this Z, and then I will give a proper definition of Hopf monads. So let's see how it works. So we start with an object of the center. So we have an object X and a half braiding. Let me draw a picture. And the object X is here. And X can cross any other object Y thanks to the half braiding. So I don't know if I'm optimistic, but I prefer when things go uphill. So that's the half braiding, and it satisfies axioms, which I have written down here. It's half the axioms of a braiding, in a sense. So by duality, we can transform this into a morphism from Y dual tensor X tensor Y to X. And this becomes dinatural, because the half braiding is natural. So if you take a morphism here, you can let it go through sigma, and it comes out here.